periods. This is the stuff that we can do from the ground, right? Okay, so we've had 2 data releases. We've published 2 catalogs. One was done in June of 2010, and the other one was done just a couple weeks ago, February of 2011. And so these are the contributions from Kepler. These are confirmed planets, and what I'm going to show you are our candidates, okay? Things, the stars that have compelling transit signatures. So this is what it looked like in 2010, and this is what it looks like in February. So already you can see that this is a game changer, right? Now, if you squint, where are most of the planets? They're between Neptune and Earth, right? Smaller than Neptune. 75% of our candidates are smaller than Neptune. There are 1,235 transiting planet candidates represented here, okay? You can see comparing the blue points here to the yellow points, that as we collect more data, we're filling in at smaller sizes and longer orbital periods, and that's what we expect. So this is the state of affairs. This was based on, we detected these in 5 quarters worth of data, which is about a year. Actually, one of the quarters was short, so it's about a year's worth of data. This is a 3.5-year mission. As we continue to collect data, we'll be pushing down towards this corner of the diagram. Okay. This is how they're distributed over the field of view. This is another skittle plot. You can see that they're everywhere. If you squint, you can see that most of them are orange, right? Which is orange and green, I guess, in here. Most of them are that size. And that's the same thing that this is just showed in a different way. This is a histogram, 662 that are 2 to 6 Earth radii, 288. We call these SuperEarths. This would be 1.25 to 2 Earth radii. Kepler 10b would be in this bin. And we've got 68 that are 1.25 Earth radii or smaller. 68. I mean, even if half of them turn out not to be planets, that's still 30 some odd new Earth-sized planets. Okay, so I'm going to take that other diagram that I showed you, radius versus orbital period, remember, and I'm just going to transform orbital period into some kind of a temperature. You know, we talked about the habitable zone. You know, that distance from the star, what temperature would you feel, right? And that's what the plot looks like. And so we go from 0 to 400 degrees. I'm using Fahrenheit. That's kind of weird. I know 200 and some odd degrees is the boiling point in Fahrenheit. And so let's show that interesting region here. It's going to be way down here. This is the region that straddles the freezing to the boiling point of water. Okay? Now let me zoom into that. There are 54 targets in that region, habitable zone planet candidates. There are 54 of them. We've got some between Neptune and Earth size. We've got one down here that's smaller than Earth, and a lot that are up here in the Jupiter regime. And this diagram will fill in again as we collect more data. There are 2 interesting things to point out. One is that, you know, we've seen the movie Avatar, right? The planet was actually a satellite of a giant planet, right, that was habitable. So we're very interested in these things that are in the habitable zone but as big as Jupiter, because they could harbor large moons. And so we're very interested in inspecting those light curves, those plots of brightness as a function of time, to see if you've got a transit signature and then another blip due to a potential moon. So we'll be looking at that very carefully. The other interesting thing I can point out is that this little candidate right here, if I had put error bars in this graph, which is what I should do, we tend not to do that this plot was used for media. We don't include error bars. They don't like to publish error bars in newspapers, apparently. It would be very large. And in the paper that we published on this data set, we told the public that the star that this is associated with, we don't have a temperature or a surface gravity for it. So we don't really know what the star is exactly. But we have some color observations that we took that make us think that it might be an M-type star. So from that, we estimated what the radius of the star should be, and therefore what the radius of the planet would be. And there were flags in the paper that alerted the reader to that. But of course, that didn't prevent the media from getting really excited about this candidate here. And in fact, there was a blog online that called this the $250,000 planet candidate or something. Everybody's eyes were on it. And including Discovery Magazine. Discovery Magazine was going to write this big feature article on exoplanets, and they wanted a whole section on it devoted to this planet candidate, which we call KOI 326. And so they wrote this article, and then they emailed me. The editor emailed me and said, can you fact check it for me? And I just cringed. I was like, oh my God, what are we going to do? So I started digging around and pulling together a story for this object. Not a story, but I went back and looked at some images that